Okay, today we want to talk about Taylor and Maclaurin series. Last time we talked about power series from the standpoint of comparing them to a convergent geometric series. And we discovered that a power series does represent a function on its interval of convergence. And it is something that we can differentiate term by term on its interval of convergence. We can integrate it term by term on its interval of convergence. We can add it to other power series, subtract them. We can even multiply and divide them. We can also compose them with other functions. So a power series is a function itself, but only on its interval of convergence. And remember, we typically will find the interval of convergence using the ratio test or occasionally the root test. Now, because the ratio test and root test require all terms to be positive, we'll have to check for absolute convergence, because if it is absolutely convergent, then it must be convergent. So, the form that we can write it in, remember that these power series end up being infinite series, and the difference between a power series and a regular series is a regular series, the terms are all real numbers, so you're adding together real numbers. An infinite series that is a power series has terms that include powers of a variable. So the primary difference is that a power series has powers of a variable in its terms. There are two basic forms to write them in that we saw last time, so let's put them back up here. These two basic forms are the sum from k equals 0 to infinity of c sub k x to the k. And if we expand that, the c sub k, these are all constants. They're some constant values. And the x's are the variable, k is the index of summation. So k starts off at 0, then it's 1, then it's 2, then it's 3, then it's 4. So expanding, in the first form we have c sub 0 plus c1x plus c2x squared plus c3x cubed, and in general plus c sub n x to the nth power. It is an infinite series, and the terms do include powers of the variable x. In the more general form, or what we typically would call the Taylor series form, you will see that what is being raised to the power, or the index of k, is not just the variable x, but x minus another constant a. This constant a is called the center of the series. So a is a constant just as c is a constant, and a is the point about which we are going to determine the series. So a is a point on the graph of the original function that we'll be looking at. Now, how does this become a Taylor series? Well, last time when we were talking about power series, we developed the power series by first looking at convergent geometric series. Now remember, a convergent geometric series has this basic form. You could have constants at the front, and if you do, then the constants may generate a different first term. The general form for the sum, the infinite sum of a geometric series that converges, is the first term divided by 1 minus r, where r is the common ratio. Now it only converges if the absolute value of r is less than 1. That means the value of r has to be between -1 and 1. What we did last time was we took functions like, say, 1 over 1 plus 2x, and we rewrote them in a form to match this convergent geometric series. So we already knew the series converged, and then we found functions of certain forms, specific types, that we were able to rewrite in this basic geometric series form. The question now is, what if we have a function that is not one of this form? Can we find a power series representation for it? Now, in order to do that, we will have to make two assumptions. Our assumptions are that f does have a power series representation, even if it's not one of the ones that starts out in the normal geometric convergent form, and that we can find the derivatives of f for all orders. So the first derivative, second derivative, third derivative, fourth derivative, 10 billionth derivative, we can find them all. And again, a is going to be the center of the same series. In order to find out if we can find a power series representation for a general function, we're going to start not with exactly the power series representation, but we're going to start to the function. And by approximating the function, we hope to be able to develop a power series form for the function. So the first thing we want to do is we want to approximate our function with a series of polynomials. Now the first thing that we want to match is, given that our center is at a, if we plug it into the function, we would get out a y value of f of a. So we need for the function a f of a, that value, to match whatever we get out of the approximation. So our polynomial, when evaluated at a f of a, has to give us the same f of a value. So the second thing we want to match is we want the first derivative of the power series, or in this case, the first derivative of our approximation to the function, we want that to match at the point x equal a. That way, if the function is increasing, our approximation will be increasing. If the function is decreasing at a, then our approximation will be decreasing. We'd also like the second derivative at a to match. So if the second derivative at a is concave up, we would like our approximation to be concave up there. In general, what we're trying to do is we're trying to show that we can approximate the function by having increasing derivatives of the function matching the value of the polynomial at that point. So this is how we are going to develop the power series, by developing a power series not as an infinite series, but in a finite form. This is called a Taylor polynomial. So when we look at the Taylor polynomial, the equation for it is the sum from k equals 0 to n, so it's finite. It also has constant c sub k, very similar to the infinite form of a power series, times the product of x minus a raised to the k power. N needs to be some counting number. This is called the nth Taylor polynomial for the specific function f of x at the specific of a, also called the center. To find the c sub k, the constants being multiplied by the finite Taylor polynomial, we need to find the derivatives of the function. So this will help us pin down what those values of c sub k are. Because remember, we will know specifically what the function is, and we have to be told what to use for the center. Or you have to be able to figure out what a good center would be, as we'll see in an example in a minute. So the first thing that we want is, this is just the general formula for the Taylor power series infinity. We're going to use an approximation by stopping at n, which means that ours will just go out here to the nth one and stop. It won't go any further than that. We would like the first derivative to match. We would like the second derivative to match. We would like the third derivative to match, and so on. Now you'll see, as I took the derivative formula of the general series, what began to develop was you began to see at the front here what look very much like, and in fact are, factorials. So you see 4 times 3 times 2. In the previous line it was 3 times 2. We would expect that in the next derivative, the fifth derivative of f, that we would have 5 times 4 times 3 times 2, and indeed we do. So as you go out, you can see that as each term comes to become the first term gets a factorial at the front. You can always add times 1 at the back of it. So in general, this gives us a formula that looks like this. The nth derivative of x, if x is an infinite Taylor series, would be here. Now if it's a finite Taylor series and it stops at the nth one, then we would be able to stop right here after the first term. Now, let's take a look at the form in this notation. So it looks like n plus 1 to the k factorial divided by k factorial times c sub n plus k times x minus a to the k. Now we said a moment ago that we would like for our function to match the approximation. So we would like our Taylor polynomial to match the function at these values. So what would happen if we put in f of, take a look at both pages at the same time. So if we're looking at the previous page where we had the derivatives, if I'm looking at the original function and I substitute x equals a, as I would when I'm evaluating f of a, then all the terms that have x minus a in them drop out, and I should get f of a equals c sub 0. What about the first derivative? Same idea. I'm plugging in the value x equals a, so any terms with an x minus a or x minus a to a power as a factor will drop out, and I get c1. So f prime of a is c1. The second derivative, notice that we now see the factorial developing on the first term as it comes to the front. In a for x, all the terms with x minus a or x minus a to a power will disappear, and I get the second derivative a equals 2c squared. Well, that means c squared has to be half of the second derivative at a. I can continue in this way, and I end up for the third derivative with the third derivative at x equal a has to equal 3 times 2c3 or 6c3. So the third derivative at a divided by 6 will give me the value of c3. In general, if I keep going, I have the following formula at the bottom, that the nth derivative with a plugged in for it will cause all the factors with x minus a or x minus a to a power to go to 0, and I will get the factorial at the front multiplied by that coefficient. So in general, the nth derivative evaluated at x equal a gives me n factorial times c sub n. That tells me that c sub n is equal to the nth derivative at the center x equal a divided by n factorial. So this gives us another way of writing down the Taylor series for f centered at a. We now know what those coefficients should be. This would be f to the k at a factorial times x minus a to the k power. Now let's see what happens when we try to use this in an equation and an example. So on the next page, you'll see that I have an example here, and what we're going to be working on is the one down here. This is approximating the square root of 19 using the fourth Taylor polynomial. So I put the formulas again at the top up here so that you could refer to them as we're going through this process. In order to approximate it using the fourth Taylor polynomial, then I want to go until k equals 4. So I start with k equals 0, and then I go to k equals 4 of c sub k. Now, how did I know to use 16 for the value of a? I decided to use 16 because it's a perfect square, and my function is the square root of x because I'm looking for the square root of 19. And 16 is the closest perfect square to 19. So I'm plugging in 16 for a. Could I have used another value? Yes, I could, but 16 is the closest one to 19, and 25 would give me a worse approximation, so would 9. They would work, they just wouldn't be as good of an approximation. That's how I chose the center A. Now I need to evaluate all my constants by finding the kth derivative, plugging in the center I picked 16, and then dividing by k factorial. So first I found all the derivatives. Now the 0th derivative, that's just the function itself, don't do anything to it. So it's just the square root. To find the subsequent derivatives, it helps to rewrite the square root in its power form, x to the 1/2. So the first derivative is 1 over 2 the square root, and so on. You can see the derivatives here. Then in this column, I plugged in the center 16, and I generated what the values were here. Let's move to the next page so you can see how I put this together. When I put them into the formula up here says I multiply c sub k, the values I found, by taking the nth derivative of the function at the center 16 and dividing by k factorial. So taking these numbers and dividing by k factorial, that will generate my c sub k's. These are the c sub k's here. And then multiplying by x minus a raised to the k power. So here are the c sub k's that I found, with the kth derivative at the center divided by k factorial, and then putting them into the fourth polynomial, the fourth Taylor polynomial. Down here you can see I've generated the values, and this gives me a final value of 4.358877. I did round off there in the 6th decimal place. On a calculator, I found the value for the square root of 19 to be 4.358899, which is actually quite close. I mean, we're accurate out to the 4th decimal place. So this is a very good approximation with only the 4th Taylor polynomial. Now let's do another example. This one will be to find the Taylor series generated by f of x equal to 1 over x at a equals 3, and to determine whether or not the series converges to 1 over x. So this time we're not finding the approximation, the Taylor polynomial. This time we're actually finding the Taylor series. In other words, we're going to allow the k to go to infinity. We're not going to stop at a finite value of n. But the steps are the same. First, you find the derivative of the function. Then you plug in the center into that derivative. And then you divide that value by k factorial to generate the c sub k constants. So our function was originally 1 over x, or x to the negative 1. And its derivatives you can see coming here. Now you'll notice I have not multiplied together some of these, because it is often only when you don't multiply them together that you can see a pattern develop. You can see a factorial pattern develop. And that is what we're getting here. We're getting a factorial develop in the numerator for the kth derivative divided by 3 to the k plus first power. So when we put this together, we can write the Taylor series by using the coefficients multiplied by x minus a to the power k. Now, they gave us that a was 3, so that makes our base for the power to be the quantity x minus 3, and then it's raised to increasing powers of k. The first one, of course, does not appear because anything to the 0th power is 1 unless the thing is 0. And then here, because it has this alternating pattern sign, we were able to write it as an alternating series. And this is the formula that we generated above. This is actually one we could have done previously, because if you take this formula and you pull one of the 3's away from the denominator and pull it out front where it becomes a 1/3 constant, then both the 3 in the denominator and the quantity x minus 3 in the numerator would be raised to the k power, and they could be written together. So I could have rewritten this one up here as the sum from k equals 0 to infinity of -1 to the k times 1/3 times the quantity x minus 3 divided by 3, all raised to the k power. And you would recognize that as a geometric form series. The first term, when k is 0, would be 1/3, and the common ratio would be the x minus 3 quantity divided by 3 with the negative power so that we get the alternating behavior. Now, this will converge absolutely, and hence converge, provided that its absolute value is less than 1. Because of the absolute value, we can ignore the alternating behavior, the negative involved, and this means that when we move the 3 to the other side of the inequality, we can pull it out by making it positive 3, that the absolute value of x minus 3 has to be less than 3. That means that x minus 3 is between negative 3 and 3, and solving this gives us that it must be between 0 and 6. Now, this is using our knowledge of the infinite geometric series to find where this Taylor series converges. We still have to check the endpoints for convergence because those are not determined by the ratio test or root test or by using it as a geometric series. So if we plug in those values into the original representation for the Taylor series, if I plug in 0, 0 minus 3 just gives me 0. So again, let me put back up the original representation. You can see at the top. And that gives me this one. I can pull the negative that's in here away from it, and that will give me 2 negative 1 to the k powers, or negative 1 to the k squared, which would make it positive, which means that basically I have 3 to the k over 3 to the k plus 1, which is 1/3. But this will just generate the infinite series of 1/3 plus 1/3 plus 1/3 plus 1/3 forever and ever and ever, and obviously it will diverge. The limit of this sequence is not 0. The limit of that sequence is 1/3, and so it diverges by the divergence test. Similarly, if you plug in x equals 6 up here to the original value, or you could plug it in this form as well, 6 minus 3 gives me 3, and that gives me 3 to the k over 3 to the k plus 1. Again, this will result in a 1/3. This one will alternate, so I will have basically 1/3 minus 1/3 plus 1/3 minus 1/3, but then the even and odd terms don't go to the same place. When you have a sequence where even terms approach one number, odd terms approach another number, then the sequence is not convergent at all. So this one also diverges by the divergence test since the sequence does not go to 0. Now we have found the power series generated by the function f of x, and our question now is, and we did find its interval of convergence, so that was for the function. Our question now is, how do you know that what this series is converging to is actually the original function 1 over x? It is possible for a series to converge to something that is different from the original function. These are unusual cases, but it does occur. So here's an example of one where the function will converge to something different. So the function here, which is defined piecewise to be 0 when x is 0, and the function e to the negative 1 over x squared when x is not 0, has a very bizarre behavior. This e to the negative 1 over x squared, the integral of that is non-elementary, which basically means we can't do it using the functions we know. It comes up in differential equations. It's part of the error function, or the complementary error function, which is a well-known function for which we have tables of values. Basically what happens here is that this function, it definitely has derivatives for all orders, for all values when x is 0. And since at x equals 0, all the derivatives would be 0, then we know what they all are there. For the Taylor series for this function at x equals 0 could be written this way. And since all the values at 0 are 0, then all derivatives at 0 are 0, which basically means that the Taylor series just becomes 0. In other words, that horizontal line, which we otherwise know as the x-axis. However, this function is clearly not that horizontal line. It only agrees with that horizontal line at one single value. That's when x is 0. So it only agrees with our function at the one point a f of a. So there are cases where there are series that do converge as Taylor series, but they don't converge to the actual function that generated the Taylor series. So this is a problem. We need to know, when does the Taylor series for a given function at a center x equal a converge to the function that generated it. So in order to determine whether the Taylor series is actually converging to the function that generated it and not something else on its interval of convergence, we need to introduce this idea of the remainder of a Taylor polynomial. Now remember, the Taylor polynomial approximation function is the Taylor series which does not continue to infinity, but instead stops at some finite natural number n. We can think of the remainder for a Taylor polynomial to be the difference between the Taylor polynomial approximation, which we could write as p sub n being, let's say, the one we did, I think we did the fourth Taylor polynomial approximation. So this could be p sub for the fourth Taylor polynomial approximation, between that and the true function. So r sub n, or r sub 4 for the one we did, would be the difference between the real function and our approximation for it. We did the square root of 19. So this is the difference between the true function, the true square root, and our Taylor polynomial approximation for it. In general, if you fix n, in other words, if you're not going to change and you're always going to use the fourth Taylor polynomial, as you get your x value closer to the center, your approximation of the remainder should decrease. In other words, I could get a better approximation if I were doing the square root of 18 instead of the square root of 19, because 18 is closer to 16, my center, than 19 was. I could get an even better approximation for the square root of 15, because 15 is even closer to 16 than either 18 or 19 is. Now, if we want to allow n to change, then we fix the value of x. So let's say I want to find the square root of 19, full stop. I don't want to change it to a different number. I want the square root of 19. In that case, to get a better approximation, or to decrease this remainder or error, I need to increase the number that I go to. So I need to increase n. I need to use a larger Taylor polynomial approximation. For all the x on the interval of convergence for the power series, or the Taylor series, then, f of x should be the sum between the Taylor polynomial approximation plus this remainder function. And there should exist some number c that's between x and the center a and I, such that we can write the following relationship. And this is a direct consequence of the mean value theorem, which, as I told you, is a most valuable theorem. So in general, what we have is that as long as we do have this relationship, then we can say that this Taylor series, which is this infinite sum here, should be equal to, or rather the function should be equal to, the Taylor polynomial approximation plus the remainder. The Taylor polynomial approximation is just stopping at exactly n plus the remainder, the error term. Our remainder can be given by this. And you'll notice when you look at it, this has the same form as what you saw in the Taylor polynomial formula or the Taylor series formula, but for the next term out, n plus 1. And instead of the center c being plugged in here to the n plus first derivative, we have this value c. C is just a number that is between x, the number we're trying to find the square root at, in our case 19, and the center a, which in our case was 16. So c is some number between 19 and 16 as a consequence of the mean value theorem. If we plug this in, this gives us the remainder. Now, the problem is we may not be able to find c. If we can't, it's hard to find c, then what we want to do instead is to find a maximum that we think those values could be. So we look somewhere and a, and we think, well, what's the largest possible value, any number between x and a, could have if I plug it into this formula. That largest value we're going to use as m. So we'll make it an upper bound on our n plus first derivative at c, where c is this number stuck between x and a on the interval of convergence. This lets us rewrite the whole thing in terms of absolute values, since we really don't know if our Taylor polynomial approximation is a little too big or a little too small. By putting in the absolute values, we can say that the remainder, which has to be the difference between the function and the Taylor polynomial approximation, has to be less than or equal to this m, which was an upper bound on the value of the n plus first derivative at c, times the absolute value of x minus a to the n plus 1, coming from our formula up here, divided by n plus 1 factorial, also coming from the formula up here. The x minus a needs to be in absolute value because, again, x could be 15, in which case 15 minus 16 will give us a negative, and we want these to all be strictly positive. Now, how do we know when this Taylor series converges to the actual function? So here is the convergence of a Taylor series theorem. Assuming that f does have a Taylor series representation and that we have all the derivatives of f on this interval containing the center a, then the Taylor series for f of x centered at a will converge to the function that generated it for all the x values in the interval on one condition, that the limit of r sub n goes to 0. In other words, provided that the limit of the remainder goes to 0 as n goes to infinity as we take larger polynomials, then the Taylor series generated by the function f centered at a will converge to the actual function that generated it. Now this is an if and only if, which means that it's bidirectional. You can go either direction. Now, granted, it can be hard sometimes to show that the limit of the remainder does go to 0, but we're going to do a couple of examples so you can see. The Maclaurin series has a center of 0. A Taylor series, the center can be anywhere. So a Maclaurin series is a special case of the Taylor series where the center A is 0. What we want to do is we want to start with the Maclaurin series for the exponential, the basic one, e to the x, and we want to determine its interval of convergence. Now, that does not mean that that Maclaurin series generated by e to the x and centered at 0 has to converge to the values of e to the x. It could be converging to a different function, so we need to determine that. So here we go. We have the derivatives in the first column, derivatives plugged in the center a equals 0 in the second column, and we've generated the constant value c sub k, which would be the kth derivative of f at the center divided by k factor column. So over here we've generated, well, the nth derivative of e to the x is still e to the x. Those don't change. So when I plug in the center 0, those don't change. I get 1 for all the values of the derivative at the center. So basically my generated values for the constant c sub k are just 1 divided by k factorial. By definition, 0 factorial is 1. So this down here gives us the generated sequence polynomial for the e to the x. So this is a Maclaurin series for e to the x. Now we need to find its interval of convergence and then determine whether or not this Maclaurin series is actually converging to e to the x by looking at the remainder. So here is the ratio test where I checked for absolute convergence because, again, we don't know which side we're on, although in this case we can assume it would all be positive because we are looking at e to the x. But again, best not to assume, best to always check for absolute convergence. Absolute convergence implies which gives us what we need. So applying the absolute convergence test with the ratio test, I end up down with the limit as k goes to infinity of the absolute value of x divided by k plus 1. K's smallest value is 0, so I don't have to worry about it being an absolute value. It's just the x value I have to worry about. Now, x does not depend on k at all, which means that I can factor the absolute value of x out of the limit because the limit only depends on changing values of k. That gives me the absolute value of x as a constant at the front. And then when I evaluate the limit as k goes to infinity of 1 over k plus 1, that goes to 0, and anything times 0 is 0. That tells me that it doesn't matter what x is, it's going to converge to 0 no matter what. Therefore, I can use any value of x, so the interval of convergence is negative infinity to infinity, which means the radius of convergence is infinity. Is it converging to e to the x on this interval of convergence? That is the limit as n goes to infinity of r sub n, the remainder of the nth Taylor polynomial, is that going to 0? Using the formula for r sub n, we take the n plus first derivative of the function at some unknown value of c, where c is between my particular x value and a, the center, and divide by n plus 1 factorial, and multiply by x minus a, the quantity, to the n plus 1 power. Now, c again has to be between the center and x. Our center is 0, so c is between 0 and x. That means e to the c has to be between e to the 0, which is 1, and e to the x. Since e to the absolute value of x is a strictly increasing exponential function, basically starting here and then increasing exponentially all the way up, then you know that e to the c has to be less than or equal to e to the absolute value of x. And again, putting in the absolute values guarantees it's strictly increasing and not a decreasing exponential. That means that I can say that the absolute value of the remainder, which is equal to this value up here, e to the c, has to be less than or equal to e to the absolute value of x, because e to the c is less than or equal to e to the absolute value of x. The other two parts are the same as they were up above, with the one added value that I put x in absolute values to guarantee it's positive, since I'm looking at the absolute value of the remainder. For a fixed value of x, then, if I take the limit of both sides, the limit of the remainder becomes the limit as n goes to infinity of e to the absolute value of x divided by n plus 1 factorial times the absolute value of x to n plus 1. E to the x, again, does not depend on the limit variable, which is n as far as the limit is concerned, so I'm able to factor it out. Now, the next part is a consequence of the relative growth theorem, which we talked about when we did sequences. And this double inequality means that factorials grow on an order of magnitude larger than x to a power does. In other words, they grow so much faster, they reach infinity so much quicker, that having them in the numerator would drive it to infinity, having them in the denominator will drive it to 0. So powers of the variable don't grow nearly as fast as factorials do, which makes this go to 0, which means that this limit here is going to approach 0. And since our limit of the absolute value of the remainder is less than or equal to that, and it's less than or equal to 0, well then it can't be less than 0 because this is absolute value, which means the limit has to be 0. And since the limit of the remainder goes to 0, then we know that the Taylor series generated by e to the x actually converges to e to the x. So what have we accomplished? What we've shown is that we have a Taylor series generated by e to the x centered at 0 that actually goes to the value of e to the x. We can rewrite e to the x as this infinite polynomial series. Let's do one more example. This is the Maclaurin series for cosine of x. Again, a Maclaurin series is just a Taylor series where the center A is 0. First, we want to find the Maclaurin series generated by the function cosine x. Then we want to find its interval of convergence. And then we want to determine whether the series is actually converging to the function that generated it, cosine of x. So we again start with our columns, the derivative first, then the derivative at the center, which in our case is 0, and then we want to generate the constants at the front of the Taylor series or Maclaurin series. Now the nice thing about sine and cosine is that they have a pattern in their derivatives that repeats every 4. So cosine starts out here, its derivative is negative sine, the derivative of that is negative cosine, derivative of negative cosine is sine, and the derivative of sine, we're back to cosine. And then it will repeat. Cosine, negative cosine, sine. Cosine, negative cosine, sine. So it's very predictable. At 0, all the ones that are multiples of sine, negative sine and sine, will become 0, which means that every other term is wiping out, because if the kth derivative at the center is 0, then that will be 0 times all the other factors in that term, and it will drop out. So basically, when we generate the Maclaurin series for cosine, we end up with this expression that you see down below. This is something that you should know or be able to generate very quickly on a test. This is an alternating series, so you'll see negative 1 to the k. And cosine has powers of, or not powers of 2, but multiples of 2 in the denominator for the factorials. I always think of it as, oh yeah, cosine is an even function, so it has even denominators. Sine is an odd function, and you'll find out in your homework that when you write its Maclaurin series, the denominators are all odd. Now, how do we find its interval of convergence? To do that, we need the ratio test. So to do the ratio test, and I will leave the expression for the series there at the top so you can still see it. I use the ratio test for absolute convergence. Make sure that when you replace k with k plus 1 for the ratio test that you put parentheses around it, because you will need to distribute them in the numerator when you're plugging in the n plus first one. When you write out or expand 2k plus 2 factorial, it can be written as 2k plus 2 times 2k plus 1 times 2k factorial, and that will cancel the 2k factorial there. We can use the subtraction rule. When you divide by bases that are the same, you subtract their powers. So this will give me x squared over the product of these two binomials. X squared does not depend on k, which is what the limit is looking at. So we can factor out the x squared, and I have the product of those two binomials in the denominator again. And as k goes to infinity, this will go down to 0. So again, my interval of convergence is in negative infinity to infinity. My radius of convergence is 0. How can I prove that this series generated by cosine of x is converging to cosine of x on the entire real number line? In order to do that, I need to be able to write the remainder for it. Now, I know that all derivatives of cosine of x have values between negative 1 and 1, which means the absolute maximum value for any derivative of cosine has to be 1. So I'm going to choose to let m be 1, and that makes my maximum value for the 2k plus first derivative of the function at that unknown c has a maximum of 1, so there's a 1 hidden here. So it has to be less than or equal to the absolute value of x minus the center, a, which was 0, that's why we just have x, to the 2k plus 1 over 2k plus 1 factorial. Remember that we are looking at the 2k remainder because that's what's in our formula up here, right? So when I wrote out the expression for the function cosine of x, I wrote the 2kth Taylor polynomial, and this is the 2kth remainder. Now I need to find the limit of that as k goes to infinity. So as k goes to infinity, unfortunately this time I cannot factor out the x in absolute values because its power is 2k plus 1. So this does depend on what the limit is looking at, so it will not factor out. But I can use that relative growth theorem again and recall that powers of the variable, which are basically polynomials, don't grow nearly as fast as factorials do. So if the denominator goes to infinity much faster, the whole fraction will go to 0. And that tells me that the remainder must go to 0, which tells me that this Maclaurin series for cosine of x centered at x equals 0 does converge to the exact values of cosine of x on the real number line, the entire interval of convergence. In other words, you have now a way to write down the values for cosine exactly by using this Taylor series representation for it. If you need an approximate value, you can use a Taylor polynomial approximation by stopping at some finite value. Also keep in mind we can do the same things we did last class time, where if I want to find the cosine of x squared, I can simply substitute the x squared, the composition function, inside my Taylor series for cosine of x by replacing x up here squared, and that will generate a Taylor series for the cosine of x squared. Now next class we'll be talking about a different kind of Taylor series called binomial series. They are basically the same thing, but they do have more applications and a little bit more notation involved in writing them down.